Oh, well, that worked well. I just clicked record at this very moment. Uh, so now everybody's in classes here. Um, so feels like forever. um, and yeah, my activities in London were more time consuming than anticipated, so I couldn't do very much to keep things moving along. Um, but the main topic for today is making sure that all of you keep things moving along. Because uh, for assignment one, uh, I've had 9 out of 10 submissions, and then some that were graded and then revised. I think I still have at least one of those I need to get to. Um, uh, so, so assignment one is almost uh, fully taken care of. Assignment two, I have received one submission out of 10. Um, so, um, so I figured that today would be a good day to see what's going on with the second one and get any difficulties squared away. Now, um, right now, if there's now some questions may involve like really digging into someone's code to see what's not working, which I'm fine with doing that today, but I want to so I may have to defer questions like that until later in the class period. But any questions that anyone has about assignment two, now's the time. Okay. So, but before that, with the Gauss Seidel Sparse, a couple of us might have that problem. Where you tell us to use the SP solve triangular instead of the inverse, how exactly do we do that? Because I know that SP solve triangular needs two arguments, and so the first argument would be D plus L, right? Right. And you would use that with what would be the second argument? Okay. Let's see. All right. All right. So I'll start a script here, and I'll post this later. Okay. So I'll just lay this out for how what's supposed to have Gauss Seidel, and hopefully this answers your question. Okay. So Gauss Seidel in matrix vector form is D plus L x k plus 1 is equal to b minus ux k. So every iteration, let's solve a lower triangular system. So the matrix in question, yeah, like you said, is the D plus L, so the lower triangle of A. And then the right side is that entire vector. So that's playing a role of your, like you're solving like Ly equals B, for instance. That whole vector is your B. Okay. So is that what was missing? Yeah, because basically, really because the function, the sparse triangular solve, can be used for either a lower or upper triangular system. By default, lower triangle, which is nice because that's what you actually have in this case. Okay. Actually, one thing that's interesting that I want to point out related to this about Jacobi versus Gauss-Seidel. Okay. Oh, okay. So here's the formula for the Jacobi method. Now, well, okay, here written in both matrix vector form and also component form. And for the assignment, it's easier to do this in component form. You can just apply this formula here. So in the case of Jacobi, the matrix is diagonal. So it's easier in that case. You don't need a triangular solve. You could just form everything that's in the large parentheses here, and then divide that by the corresponding diagonal entry of A, whichever diagonal entries of D. So this 1 over AII is the multiplication by the inverse. So it's pretty much the only time where it's okay to form the inverse is when it's a diagonal matrix, because you're just reciprocating. Okay, and then by contrast, Gauss-Seidel, okay, here it is again in both forms. So this is what I showed you earlier, and then the component-wise form. So here again we have a 1 over AII, and then we have everything here in that's being divided by AII. Now, you can think of this as Jacobi method with one tiny change. In the Jacobi method, this k plus 1 would just be a k. So with that in mind, because Jacobi and Gauss-Seidel have such a small change between them, just an index in a way, or you're accessing certain numbers from a different vector, it's quite obvious that the number of floating point operations required by an iteration of Jacobi or iteration of Gauss-Seidel are exactly the same. But in Jacobi, you're solving a diagonal system. So you're just dividing by n diagonal entries. It takes n operations. What about a triangular system? How many operations does that take? Like, we talked about like how certain algorithms in linear algebra are order n squared, order n cubed. What is it for this forward substitution here? Which one is that? No, it's order n squared. Yeah. Actually, for general triangular system, it's exactly n squared. So what's interesting is here you have to expend order n squared work to solve a system, whereas in Jacobi it's order n. Yet the number of operations overall is exactly the same, which seems kind of contradictory until you realize that in Jacobi method, you have to do all this work to make the right-hand side. You have to do all this. That takes order n squared work. And to go from Jacobi to Gauss-Seidel, all you were doing here is you are shifting half of this order n squared work from matrix vector multiplication to forward substitution. This is part of a forward substitution algorithm. It just looks kind of like the operations you perform in matrix vector multiplication. So, yeah. So these are the nuts and bolts of these methods. So in either case, both methods, also with SOR, you have to do a matrix vector multiplication up front to get to right-hand side to solve your system. Okay. The same thing happens. Well, we talked about this in an earlier class with time stepping. We saw like methods like forward Euler, backward Euler, and Crank-Nicholson. Crank-Nicholson method, you have to do a matrix vector multiplication first, then solve a system every single time step. Whereas with forward Euler, backward Euler, you're either solving a system or doing a matrix vector multiplication, not both. Okay. Other questions about assignment 2?
I just tried it and I'm getting an error about the shapes of my vector. So this was a problem I was having before, but I was able to fix it by reshaping.
Uh-huh.
Did you have to reshape your x naught when you were doing the?
Or it may have depend on how you created it in the first place.
Okay, I think I created it the way you had done it before, where it was just zeros and
Yeah.
linked in. But I
Um,
had to end up reshaping it to be a column vector instead of a.
okay. So this is in the process of forming at right side. Are you doing like a matrix vector multiplication? Or because another way in Python to do matrix vector multiplication is to use dot.
So maybe try that.
Yeah.
I also tried that and I was also getting that error. And I think it was also because the B that you gave us was a row vector. It worked everywhere else, but for some reason when I was trying to do it, we had the same issue.
Yeah. Or I may not have created a row vector, but a one-dimensional array. That would be the now. Okay, so, like this something in the code that I given. Okay, let's take a look at that. Okay. Okay, you mean like this? Okay.
See, I didn't have any problem with the way that was set up for Gauss or Jacobi.
Yeah.
But when I got to the Sparse, I started getting that error, even when I tried to do dot. So I had to end up reshaping B in my.
Okay. And so did the error occur for matrix vector multiplication?
I think it occurred for both. I think I also tried to do dot, and I think I.
Okay. All right. Let's try investigating this. Just out in general code. So if I make a matrix here, okay. Okay, and what I want to do is a random matrix. Okay. Let's make this a little bigger. Okay. Okay, so here, this is a function I want. I just have to create a random sparse matrix to try this out on. Okay, so I'll make a 3x3 sp.rand 3x3 density. Let's say 0.5. Format equals compressed sparse row. Okay, so now we have. Okay. Oh, whoops. Oh. Okay. I want to compute the determinant of this matrix. I can't compute a determinant on a sparse matrix, but A.2array makes it a full matrix. And sure enough, its determinant is non-zero, so at least it's non-singular. Okay, so now I have this 3 by 3 matrix, and then I'm going to make a B. I'll just use this exact B right here. Okay, so if I try this, oh, let's try that again. All right, if I look at Y, it doesn't know what to do with that. That's strange. But A times B worked in my case. So, yeah. Yeah. Now, okay, I want to try to decipher this Y here. Oh, okay. I think I know what's happening in this case. If I look at A, oh, that's freaky. Okay, so A dot AB is not A times B in this case. So what it's doing is it's A times the first element of B plus A times the second element of B plus A times the third element of B. So it kind of is a dot product in that sense, where it's so it's taking A as a single entity and dot producting it with B in that sense and adding them together. So, but not really what we had in mind. Now, if I'm going to go do a different B here, I'm going to make it a column vector. Now, for a column vector, I need to make each element its own row. So that it's so this is literally a 3 by 1 matrix, a two-dimensional array. So let's try the same operations. A times B2 as opposed to A times B. Notice the elements are exactly the same, but whereas B is a one-dimensional array, and the result A times B also a one-dimensional array. This is exactly what you should expect. That it's realizing, oh, it just wants matrix vector multiplication. We'll return a result that has the same storage as the original vector. Now, here too, A times B2. B2 comes in as a column vector, and then the output also a column vector. So star seems to be behaving in a reasonable way. Now, what if I try numpy dot 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 A with B2? I think that's going to behave the same way. Oh, it doesn't like that. It won't, because before it would let me convert it to an array. Okay, let's try this instead. If I do print y2 of 0, yeah, so that's a 3 by 3 sparse matrix. Although, now that I think about it, sorry, okay, I apologize. I goofed. It did not add them up. So, okay. All right, so B is a vector. In other words, a one-dimensional array. Actually, let me edit that. 1D array or 2D array. Doesn't seem to matter which one. That it seems to be basically an array of matrices which are A scaled by entries of B. It didn't bother adding them. So that seems to be awfully non-intuitive behavior of dot. Unfortunately, I wrote my solution so long ago that I had to go look back at it, which I'm not. I'll do it during a break. Okay. I I like to use star whenever I can, but yeah, but it seems. Whereas if I make if I convert the sparse matrix to an ordinary matrix, okay, oh, that's even worse. All right, so here's my full matrix, and I multiply that by B. Okay, that is the same matrix vector multiplication that I got earlier, but for some reason, times B, it just brings you the same matrix back. That doesn't make sense. If I multiply it by B2, it, which is the column vector, wow, it's like nothing is behaving correctly at all.
And that's the problem I had. So I had to like do reshaping and stuff because transpose. I know we talked about transpose before, but
Yeah.
I wasn't able to transpose any of my vectors, and I was thinking maybe I was going to ask you to revisit that too because transpose wouldn't work for me anywhere.
Yeah. That's.
Have that, like for example, maybe if you try to transpose your B or your B2, it never works for me. I tried to
Well, I've seen that transposing doesn't do anything if it's already like a one-dimensional array.
so no way around that
Uh,
other than reshaping.
Yeah, either reshape or some way of making it into an actual 2D array. That's when transpose actually has meaning.
So he has to actually do that reshaping because we tried that.
Yeah.
We tried transpose.
Mhm. Yeah, so this right here is honestly rather troubling because I've often used matrix vector like star for matrix vector multiplication or dot, and uh, and everything seems to work just fine. Or sometimes I'm able to use them like interchangeably.
And it worked for me sometimes. So when I ended up doing the Gauss Seidel sparse, it won't work for me if I try to do the triangular thing. But if I
Yeah.
use the inverse, then it works fine with
Yeah.
the star. But it won't work with that triangular.
Yeah. So now if I do okay, if I look at dot B2 as opposed to B, okay, so it's kind of weird that with the sparse matrix, star seemed to work just fine, whereas if full matrices, only dot seemed to work just fine. Like, get together, Python. Jeez.
Well, I think that's what we call public domain.
I guess so. Yeah.
On the bright side, it means there's a possibility to create another library that works.
in a sensible way. Yeah. Okay. So, and who knows? I've seen it happen sometimes where MATLAB, after a long session, will get confused and start producing nonsensical results. Then you restart it, and it behaves again. I don't know if it's a similar phenomenon that we're having in Python, but ugh.
But I thought that problem in MATLAB was a storage problem. I might be wrong.
I don't know. You know.
Don't.
Yeah. I never bothered looking up into It probably is, yeah. But like memory leaks and all that sort of thing. But okay, so it seems like the only advice I can offer in this case is if you're dealing with full matrices, use dot. And it's, yeah, because wow, because if I'm just doing, oh wait, yeah, a full, yeah, like how is this sensible? That is saying like, oh, I'm just multiplying it by the first element of B. Now, if I look, for instance, at the various pages that get into how to perform MATLAB operations in Python. Okay. Well, right. You know what? I had taken advantage of this for vectors or one-dimensional arrays. That in MATLAB, for instance, you want to multiply vectors component-wise, you have to use dot star. If you just use ordinary star, you can't do it in MATLAB. It's an error. In Python, it does element-wise multiplication. Okay. Now, there's a matrix type, which we never bothered with because they recommend just using NumPy ND arrays most of the time. And there, it behaves like you would expect it to. Okay, so that explains why for full matrices, for NumPy ND arrays, you should not use star. It has an entirely different meaning. Although, whatever meaning it came up with for what I just did, yeah. So, okay, these aren't links. I can't look them up that way. And then it's just a totally different situation for sparse. Now, okay. Oh, there's an at operator since Python 3.5, which I believe is what I have. So what if I try this? A full at B. Oh, okay. You can do that. So, matrix vector multiplication. Actually, I believe this applies for just matrix multiplication, including matvex, short for matrix vector products. So for NumPy ND array, use the at sign. But apparently with sparse matrices, okay. Yeah, so really, or dot. so at sign is the less cumbersome version of using dot. Only because star is already reserved for meaning component-wise multiplication. But apparently results cannot be very well predicted if you're doing component-wise multiplication on objects of different sizes. It just doesn't seem to know what to do in that case, which is also kind of aggravating. But again, take MATLAB for instance. MATLAB has made changes in how their operations are interpreted. For example, in MATLAB, suppose you had a row vector and a column vector, and you subtracted them. It used to be an error. Now it just takes element-wise differences of them. And there's other changes like that they've made and maybe not communicated so well, and over the years. So we have to be aware of these things. Okay. Now, on the other hand, for let's see, with sparse matrices and operations. Okay, here they don't. Okay, where do we talk about the operations you can perform on them? Okay. Because here they tell you can use dot. Oh, dot. I see. Warning. Do not use NP dot dot or NumPy dot on sparse matrices. It doesn't know what to do with them. Okay. However, there's a dot method of sparse matrices that does have a desired effect. Okay. So, let's revisit this. So, A is my sparse matrix, B is my vector. So I do this. A dot dot B, and that produces a decent result. Okay. So for sparse matrices, use dot star or dot method. So in other words, don't do np dot ab, do a dot dot b. Okay. Well, this has been joyous. All right. Let's see. Okay, so at least we now know the appropriate approaches, or the intended approaches, or I guess what's sanctioned for matrix multiplication in both cases. And not sure if it helps or hurts matters that it's there's multiple ways of doing each. Okay. All right. Now, and yeah, it's in fact for both full and sparse, there are two different ways to do that are all different. So, yep, open source indeed. Yeah, well, but I guess there had to be some discussion among various individuals to settle on this, and I'm sure we must have gotten pretty acrimonious. Okay. Other questions? Okay. And this is still with the Gauss Seidel or the. Okay. Is it getting the same error or?
Yeah, it's saying something about the shapes, but I'm trying to print out each part to see what the shapes are. Because it's saying that both of them are like a 1 by 3, which would make sense why they won't multiply, but I don't know why they're 1 by 3. Because when I actually do the triangle,
Yeah.
it's actually 3 by 3. But when I do it in the front, it's saying that it's 1 by 3. I don't know what's going on. It's supposed to be 3 by 3, right?
Of a matrix coming in, yeah. Yeah, it should have like the vector coming in should either be a 3 by 1 or maybe a one-dimensional array of length 3. So how row vector comes out of all that, I have no idea. Okay. Is anybody else experiencing that same problem? Well, I haven't looked at your code if you turned in, but
well, I got something I thought looked right.
Okay, all right.
I may be experiencing that problem, but I should probably.
So you do not have this difficulty.
Well, I had a whole bunch of difficulties at one point, and then it started spinning up things that looked kind of right.
Okay.
And I said, well, here, it's the due date. I think I'll submit it.
Okay. All right. All right. Well, we can take a look at that later. Anyone else have some kind of puzzling behavior?
However, I can say one thing I did do in my code assignment to is converting everything to the same kind of sparse matrix. I forget exactly which type.
Same storage convention.
So that it would work. I had just wild difficulties not doing that.
Oh, okay.
So, yeah, a little bit.
Interesting. Okay.
So in the end, I decided that the proper way to do all these kind of matrix decompositions was just sparse.
Yep.
Ignore the full stuff. It's harder to look at.
Yeah. Okay. Yep. Alrighty. Wow. All right. Well, we'll take our first break at this point, and then I'll shift gears after that.
So when we
Oh.
that inverse thing.
Yeah.
Okay, I got it to work now using the triangle. I was under the impression that from your note, based on the formula, that you know how it does the d plus l inverse and multiplies it times your
Yeah.
other stuff. So if you use the triangular, you don't have to multiply it by anything. You're just solving.
Right. Yeah, because that's the effect of multiplying by the inverse.
But I still had to. But if I don't reshape b, and if I don't reshape my initial vector, I do get an error. But by doing that, it does work.
Okay.
But my conjugate gradient, it's just like one long row vector, which is not correct. But I followed the algorithm, so I don't know what's going on.
Ugh. I'm still recording. I'm debating whether to leave recording or not because if I make separate videos and I splice them together at the end, then it takes forever to save it and also to upload it. I think how difficult that would be is another matter. Yeah. Okay.
Well, it all depends upon the movie editor that you're using.
Yeah, because I was doing this all in QuickTime Player and.
Oh, good Lord, that's.
Okay.
Oh, yeah, that's gonna be hard. But anyway, the fast forward was created on YouTube for a reason.
Yeah, exactly. Okay. All right. Well, to those of you who are watching at home, I'm going to leave this recording, and so as David was just saying, YouTube is fast forward for a reason, and feel free to use accordingly. But when I come back and resume in just a little bit, I'm going to switch over to back to Spider, and you'll looking at code in there. So I'm just going to leave a course web page up like you have now. So when I switch from that, that's how you know how far to fast forward.
So Dr. Mendel, I have successfully created a matrix multiplication algorithm that takes n to the 12 n steps.
N to the 12?
Yeah, n steps, yeah.
Wait.
Yeah, you know,
wait, so say n to the 12 n?
Yeah.
So 12 n is the exponent?
Yeah.
How's that possible to make it that much slower?
Well, it's a miracle.
Okay. That's kind of freaky.
No, but I hope my little notes kind of suggest where I'm getting that there might be a possibility of approximating.
Right.
That's significantly less. I don't know if it's the magic 2, but
I hope it's significant enough.
well, it's significantly less than 12.
Yeah. Okay. That's a start. actually keeping track of time.
So when we do conjugate gradient, actually doing dot T will do the transpose, right? That we need to do.
Oh,
Because the algorithm has T, that's a transpose.
oh, well, for a dot product though.
Dot T won't work.
Well, you can. Okay, hold on. I guess we're somewhat resuming class here. Okay, so, all right, so yeah, the transposes in the conjugate gradient are solely for purpose of computing dot products. So then you're dealing with two vectors, which would be like one-dimensional arrays. So you would use dot.
So we don't have to actually do the.
Yeah, you don't actually have to carry out a transpose.
I wonder if that's why it's not converting.
Oh, okay.
So everywhere I have a T, I don't have to put transpose.
Right. Well, since you're dealing with one-dimensional arrays, a dot T probably wouldn't really do anything anyway.
So would you just be doing the dot product of that in itself?
Right. Yeah. Let's see. That reminds me of something I wanted to check on here.
It still doesn't work, so I guess it didn't make a difference.
Okay. Oh, so there's some other issue. Um, oh. Okay. 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 Well, someone needs to get their keister back in here. Dang it. Okay. All right. Well, actually, I think that was an unexpectedly long break, so that'll be our only break. So I have a couple other things to demonstrate, and then whatever time is left over, we can see if anyone has any, I guess, questions of a more individual nature about assignment 2. Okay, now, so last class, last time we had class here, I did something involving images. So I'm going to do something else involving images. Okay, and this has to deal with compression of images. So one thing that's kind of weird is I have here, I'm using a different image. So I thought in case Haley was tired of seeing herself on screen during class. And so I have an image left over from one of my old research projects that shows a boat in the harbor. And this one's a PNG, portable network graphic. I've had some difficulties working with PNGs before, where I would pick them apart and try to work with them. Like they wouldn't display right. But I didn't have what?
Hey, is this just a Python problem with PNGs, or is this also a problem?
What it probably is me incorrectly using some Python image functions. Because like if I would load an image like this into MATLAB, it wouldn't be a problem. But here also with this PNG, I did not have any difficulty either. And it may have to deal with color versus black and white or grayscale. This is a grayscale image file. So maybe when I loaded a color one, I need to see, because if I'm using the regular way that Python recommends, like using get data and then convert to a list and so forth, yeah, that wasn't working right. It worked just fine for JPEGs, but not PNGs. Still haven't resolved that yet. So maybe during one of our few remaining class sessions, I can take a look at that. So what I'm doing here is I want to contrast working with a grayscale versus a color image, because the first few statements right here, I'm opening the image in the same way as I did with a previous color one, using image.open from the PIL package. Get the width and height. This part also is the same as before. We're using get data on the image, convert to a list, and then make sure of a floating point number. So now I have a NumPy ND array, a one-dimensional array of all the pixel values. And if I were to print out the shape, okay, put a separator in here. Okay. If I were to print this out, it would show me that it was just the length, like so the width times the height number of elements, and then I can go ahead and display that. So I did not need to, whereas with the color image, it would be something reshaped into an m by n by 3 array, and you would get all these, so you have these 3 slices for RGB. That doesn't apply in this case. Okay, now what I'm doing here is using from the scipy.linalg is the SVD, the singular value decomposition. And which has come up in other classes. A is equal to U S V transpose. A is m by n. U is m by m, the square matrix, and it's an orthogonal matrix. S is m by n, the same size as A, is a diagonal matrix. V is n by n, also orthogonal. So S, or diagonal of S, are singular values, always non-negative. Always, and by convention, ordered from largest to smallest. Okay, so I'll label these S1, S2, up to SP, where P is a minimum of M and N. R, which is a rank of A, that is the number of non-zero singular values. Although, due to round-off error, it can be, you may have a situation where a singular value is incredibly small, because it's really an approximation of a lower rank matrix. Okay. So columns U1, U2 up to UR are an orthonormal basis for the range of A. And V, R plus 1, R plus 2. So these columns of V are an orthonormal basis for the null space of A. So the U's, the columns of U are the left singular vectors, the columns of V are the right singular vectors. But how this helps us for compression is the best rank K approximation of A is you take the largest singular value, corresponding left singular vector, and then a transpose of a corresponding right singular vector, and then you keep going. Same thing for the second singular value. And you keep going all the way up to SK, UK, VK, transpose. So here we have K terms that are the best rank K approximation. Now, what that means is if you let this go all the way out to R, the rank of A, that's all of A. That's exact. So the storage is K times M plus N plus 1 to store all of those singular values, those K singular values, those K left singular vectors and the K right singular vectors, versus M times N. So if K is very small compared to M and N, then you've achieved a lot of storage savings. Okay. The error in the rank K approximation, try to get some measure of that. Use the fact that the 2 norm of a matrix A is equal to the largest singular value. So in other words, for any matrix A, you compute a singular value decomposition. The 2 norm is just the largest singular value. So that means that the 2 norm of the error, A minus AK, so actually I'll label this AK as the rank K approximation, is just equal to the K plus first singular value. So that gives some measure of the accuracy. So this would be like the absolute error in this rank K approximation. Or you can divide this by S1, so then you get relative error. So it's the norm of A minus AK divided by the norm of A. Okay. So what I'm going to do is, in this code that follows, I'm going to compute rank K approximations of this image, starting with rank 1, rank 2, and so forth, and display them each time. Now, if you only take a rank 1 approximation, that's generally not going to be a good approximation of the image, and that will literally show as a bad approximation. But as I keep increasing a rank, you'll see it get better and better. Okay, so here I go ahead and use this function from scipy.linalg to compute the SVD. Now, what's interesting is in the MATLAB, you do this, USV equals SVD of A. So the usage is very similar, but one thing I have to point out, it's very important. MATLAB function for singular value decomposition returns V. SVD in Python returns V transpose. So you want to access the right singular vectors of A. In MATLAB, you would take the columns of this third output. Here you would take the rows. So okay. All right. So then, well, now that I have a singular value decomposition, I want to plot the singular values. on a logarithmic scale. I want to get an idea of how rapidly they decay to 0. That would give me an idea of how many terms I actually need to keep. Because generally the matrix is going to be full rank. It's that some of the singular values are very small. You can neglect those terms. But a lot of times for images, just keeping a relatively low rank approximation is enough so that visually the image pretty much looks the same. Okay, so we'll go ahead and take a look at expect those singular values. And now what I'll do is, in a loop, I'm going to compute the rank K approximation. So here I take the K singular value, that's the SK, because that's just a one-dimensional array of singular values. And now, notice in this formula, mathematically, I have U1 V1 transpose, U2 V2 transpose. That is called an outer product. So to distinguish, inner product, U transpose V. And we can use NP dot dot U and V, as we saw from earlier in this class. that thankfully works. Okay. Well, now that I think about it, I want to try something here. I'm going to make two one-dimensional arrays. Okay. All right, so presumably if I do np dot dot u and v, okay, so 3 minus 8 is minus 5. Okay, so that's the correct value. So that's a dot product. What if I now, on the other hand, suppose I create these not as I want to make them as column vectors. So each element is its own row. That way I can transpose actually has a meaning. All right, so here's U and here's V, column vectors. So first one, try dot. I'll see. Okay. Doesn't like that when they are column vectors. On the other hand, suppose I do this. The dot product would be U transpose at V, and it gives me a 1-by-1 matrix. So this carries out proper matrix multiplication. And minus 10 is the correct result. What if I try this? NP dot U transpose V. Okay, and that does the same thing. Okay, so in a way this makes sense that because, well, yes and no. I was hoping a dot would be smart enough to realize, oh, there's two vectors of the same length. It wants me to take the dot product of them. Let's go ahead and do that. But it doesn't do that. It's just whatever. It's following the rules of matrix. It's only smart enough to do that if U and V are one-dimensional arrays. If they're two-dimensional arrays, then it treats them as matrices, and it follows the rules of matrix multiplication. That's why I raised the error when I did that. So to summarize, forms a dot product of 1D dimensional arrays. Forms matrix multiplication of 2D arrays. So that's why dot of U and V works if they're one-dimensional arrays, but if they're two-dimensional arrays of the same dimension, like both row vectors, both column vectors, you must transpose them to use with dot. Okay. All right. So that's the inner product. The outer product has UV transpose. And that equals M by N matrix. M is equal to the length of U, N is equal to the length of V. So by contrast of inner product, because a transpose is applied to the opposite operand. So here the transpose is between a U and V. Here the transpose is on the outside. Now this notation here is assuming that U and V are column vectors, as is normally the convention in linear algebra texts. So what I could do is, okay, so here I have my vectors U and V. So I did U transpose V earlier. If I do U at V transpose, that is an outer product. So that's one way to do that. The other possibility is if I create U and V as one-dimensional arrays, like I did before, I can do this: np.outer U and V, and that has the same effect. So you can use a NumPy function outer for outer products. Okay. Now, alternatively, if I do these as two-dimensional arrays that happen to be vectors, and I want the outer product again, I cannot do outer U and V, but I can do outer U and V transpose, and that also will work. Okay. Just like with the at sign. And that's actually what's happening here. I have a column of U, that is a left singular vector, and a row of V, that is a transposed right singular vector. So the transpose is already built in to what the SVD function returns. So that's why I didn't have to do any transposing here. It was already done. So this gives me one term of a rank K approximation. So I just keep accumulating all of these terms. I'm going to compute the error, which is the next singular value, divided by the largest singular value. So this is a relative error in this rank K approximation. So like I can think of it as like a percentage error to see how accurate my rank K approximation is. And then, okay. And then I'll go ahead and show it. And I'll give myself a pause. I want to see each rank K approximation. Okay, so any questions about what this code is doing before I actually run it? Okay. So I don't recall if I had imported in this particular console session. Okay. Okay, so this is the total number of pixels, 262, 144. This is 512 by 512. So here is the original image, and here are the singular values. So I wish this was bigger. It kind of bugs me. I wonder if it'll be better if I run it out here. Okay. Oh. All right, I need to put an extra line here. Okay. Okay. see if I can make this even bigger. That would be nice. Oh, I can. Great. Okay. So here's the original. Let's see, are there any other? I want to see the. Oh, okay. So I have to close this. Okay, here's where it shows me the singular values. I'll take a closer look at that. So the largest one, pretty dang large, like close to 10 to the fifth. Looks like around like maybe 70,000 or something like that. And then after maybe like 20 or so this is a 512 by 512 image, so there are 512 singular values altogether. But after the first 20 or so, we're already down a couple orders of magnitude. And by the time we get to 100, we're down to like in the hundreds, and then going down rapidly from there. So let's see what happens because of this rapid decay. It would take a low rank approximation of the image and see how it looks. So here is our rank 1 approximation. It's a bit off. Surprised the error is only 12%. Go figure. So, okay. And I think the way this is going to work is it's going to require me to close this. Okay. Yeah, I'll have to close each one successively. So that's the rank 2. It only knocked down the error by a little bit. Okay, so every time I close one, the next one's going to pop up. I'd like to get this down to around 1% error. So this is rank 3. Okay. All right. That's strange how that time it required me to hit enter. Oh, because I think because I had hit enter a few times before, and that was finally being taken into account. Okay. All right. So let's get to. Now we're starting to see something vaguely resembling a boat, and we're down to 7% error. Okay, let's do a few more. So at least we're okay. All right. So how many singular values do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's do one more. Okay. So this is a rank 10 approximation. So you can kind of see a boat in there. We're down to 3% error, but let's get it down to 1. Okay. Unfortunately, the error is decreasing kind of slowly. A more accurate representation of the error might be, instead of using the 2 norm, possibly the Frobenius norm.
Yeah.
The Frobenius norm of a matrix is the square root of sum of squares of its singular values. So that would better take into account the decay rate. Okay, we're just at around 2% error. What I probably should have had my loop do is also print out K as we go. Okay. But we see that we're doing much better in terms of being able to recognize details of the image. As far as how to rank, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13. Wait. $33, 37, 38, 39, 44. So this is a rank 42 approximation. So still less than 1/10 of the components, which are 512 altogether. So if I do,
So does that mean that that's how big the matrix is that represents the image?
well, in terms, it would be the minimum of a width and height. It would be how many SVD components you can have.
So you start out with 512 by 512.
Yeah.
And now you're saying I want to store it smaller, so you can literally store it in, what did you say the K value was, like 42 or something?
Yeah. So the 40, whatever rank you keep times width plus the height plus 1 for the singular values. Just to store those singular values in singular vectors. But then you'd have to reconstruct the image from that.
So it's kind of like zooming out and saying, what level can I zoom out and still distinguish the detail?
In a way, yeah, because, okay, so here we are now at roughly like rank 50 or 51, and that looks quite good. And so the storage and all that would be, okay, so, all right, I'll interrupt this. So 512 squared, that's how many, well, what? Okay.
But this is grayscale.
Yes.
And so the equivalent in color, you have to like do it separately and add it back together.
Right.
And see how much of the actual color image is still there.
Right.
Which makes it totally different.
So if I do like rank 50, 512 plus 512 plus 1. Okay, so here's how many numbers I have to store in this low rank form compared to the usual form. So about 1/5 in that case. I probably could have settled for less. I've seen some images where you actually only need even fewer terms to have a visually reasonable approximation. It just depends on how detailed the original image is. So this is one way of a very simple way of achieving some compression is using a low rank approximation. Okay.
If you put noise in your image and you did this, would it automatically remove the noise?
Probably could to a point, just because there's pure speculation on my part. I haven't tried this, but yeah, if the noise really comes from variations in singular vectors corresponding to small singular values, that it probably could have some kind of effect like that. Okay. All right, so I'll go ahead and post this code. So now we see how to do outer products as well as inner products. Okay. Okay, so that's one thing I wanted to show today. Here's another. Using a fast Fourier transform. So, and I just have a little snippet here. So here I'm making a vector of function values of just sine x on the interval 0 to 2 pi with 16 grid points. So the x values include the left boundary point at x equals 0, but not the right boundary. So x equals 2 pi is excluded due to periodicity. We don't need it. Okay, so here n is number of grid points, equally spaced. Grid spacing on the interval 0 to 2 pi. I have a parenthesis here to indicate that 2 pi is excluded. And then vector of function values. So I take a function sign, vectorize it, so I can apply that vectorized function to my vector x. And then I have a subpackage of numpy, numpy.fft. So I'm importing that and calling it npf. So from that, I'm using their FFT function to compute the fast Fourier transform. So if I go ahead and run this code, okay, and let's take a look at what we have. So first for f, all right, that's a little difficult to decipher because of the way it's being formatted. I'd rather see this as a column vector. So if I do this instead, reshape it into shape that has n rows and 1 column. Now it displays it as a column vector. So then we see the values of sine x at equally spaced points. At x equals 0, pi over 8, pi over 4. Some of you might recognize that as square root of 2 over 2. 3 pi over 8, pi over 2, etc. So all values of sine x. Now, if I take a look at the FFT results, so I do the same thing with TF, and let's see what those numbers look like. Now, they're complex, so we have a real part in the first column, imaginary part in the second column. Notice most of them are incredibly small. Well, actually, all the real parts are small. The reason why is sine x is an odd function. So when you're doing an FFT of an odd function, the real parts will be 0. If it's an even function, like cosine, then the imaginary parts will be 0 or round-off error. But in the imaginary parts, almost all of them are essentially 0 also, except for the second one, which is minus 8, and then the second to last one, which is plus 8. So I want to compare this to the same operations performed in MATLAB. So if I do n equals 16, spacing, here are my x values, and here are my function values. If I use its FFT, again, complex, and sure enough, we have a minus 8i down here, and then a plus 8i over here. So MATLAB's and Python's FFT are doing the same thing, so that's nice. Now, what is it actually doing? So the formula for the entries of TF is that TF of K is equal to a sum j equals 0 up to n minus 1 of exponential of minus I, where I is the imaginary unit, and then I have omega, okay, I k 2 pi j over n times fj. Okay. All right. So okay. So what it's doing is so it's multiplying all these by various values of sine x that I have, and because sine sine x is equal to e to the ix minus e to the minus ix all over 2I. And this comes from basics of complex numbers. And these functions, e to the ikx, or k is an integer, those functions are orthogonal on the interval 0 to 2 pi. So what's happening here is basically the FFT is a dot product of each of these complex exponential basis functions with your function f. Because these basis functions are orthogonal, most of these dot products will be 0. So only the dot products with k equal to plus or minus 1 are going to turn out to be non-zero. So that's why we got the result that we did. Now I can also do the inverse. F2 is npf.ifft, and MATLAB has the same thing, ifft function, of tf. And I want to print that as a column vector. And here we go. Now, these are essentially the values of f, except there's some round-off error involved. Like the first value is supposed to be sine of 0, which is 0. Instead, it's something times 10 to the minus 32. So we do have some unfortunate round-off error there, but otherwise, the result is correct. So for inverse, all right. So what I'm just showing you here is fast Fourier transform. The inverse FFT formula is very similar. It's equal to the sum So the only difference is we don't have a minus sign in the complex exponential. And the other difference, we have to normalize. We have to divide by n. So that's what is actually being computed. Let's see. Okay. Now, the other thing here is that the values k that I have in here, actually, I'm going to change my notation for inverse FFT. Because I'm using j to index in physical space, like your function f. I'm using k to index in frequency space. Okay. All right, that'll work. I think what I was getting at here. Okay. That the values of k here, like I was saying earlier, are referred to. You think of those as frequencies or wave numbers, and those are actually periodic too. It's customary to think of these as a set of frequencies on an endpoint grid as ranging from minus n over 2 plus 1 to n over 2. TF of k is an approximation of inner product of, so we think of these in terms of functions of x. So inner product on the interval 0 to 2 pi, of f of x with e to the I k x. Because 2 pi j over n is equal to x sub j. So this is just the x value. But it is multiplied by, so because the inner product would have 2 pi over n in front of it, which we don't have here. Okay. All right. Because the inner product is an integral of f of x times the conjugate of e to the I kx. And wave numbers are n periodic. So k equal to n over 2 plus 1 all the way up to n minus 1 actually correspond to frequencies where if you take these values and subtract n from them, you get minus n over 2 plus 1 up to minus 1. Okay. So in other words, and I point out the periodicity because if you think in terms of a grid spacing going to 0, like, and in terms of a summation representing an approximate integral, what integral is it that you're actually approximating? It's the inner product of e to the I kx. So in other words, TF equals components of f of x in basis e to the I kx for k equal minus n over 2 plus 1 all the way up to minus 1, 0, 1 up to n over 2 in the case where n is even. If n is odd, then it would go from just minus n over 2 to n over 2. The point is they're going to be integers. Okay. It's particularly important for anyone dealing with KSS methods to understand these things. Okay. But the storage corresponds to k equals 0, 1, so the non-negative ones first, then looping back around. And both MATLAB and Python FFTs work in the same way. So I'm relieved that they follow the same storage convention. But you know, it only makes sense. Okay. All right. It's just that when you're on an n-point grid, and look at e to the I kx, if you were to like plot it, for instance, in a complex plane, if you add multiples of n to k, you can't tell the difference. And the reason why is because you're not sampling these functions often enough to see what the difference is. Okay. All right. So now we have the ability to use FFT and IFFT. There are higher dimensional FFTs and inverse FFTs. So all of that is under this package, the subpackage, numpy.fft. They're all in there. There's also a version of the FFT specifically for real input values, where it takes advantage of certain symmetries to reduce the storage of the output. Yeah, so it cuts it in half. Okay. Just because if I replace here k with minus k, all it does is give you the complex conjugate in a case where f is real. So the real versions of FFT functions take advantage of that to reduce storage. Okay. So questions about this one? Alrighty. Well, I don't have any more new material today, But I figured we can use the remaining time for any further questions that anyone has, or individually or anything like that. So, well, does anyone have any questions they want to ask out in the open about assignment 2? All right. All right. Well, I'll stop the video here. Oh, what? What? Well, assignment 3 is a project, unless you want to do something. Unless you want to do something else, like David's doing. Yeah. That sounds like my default. Yeah. We don't have time for anything else. I think August 1st. Something like that. Yeah. Yes. All got to be done by then. Okay. Okay. You have a question? Okay. So I'm not sure how much more I will have in terms of new stuff, because also I want to make sure that you guys are able to get the existing stuff done. So we'll see what it means as far as class periods and so forth. If I may decide to have certain class periods just be like, well, we're not really going to meet, but I'll be here in case anybody needs help with things. For now, we'll assume that we will have class. It just depends on whether I have something else useful to demonstrate. But my main concern now is that you guys get all the stuff done, because kind of behind. Okay, so we'll see how that goes. So if I end up at like upcoming class day, we only have 3 class periods left anyway. If we're not going to have class, then I'll email you guys. But for now, we're still a go. Okay.